Assalamu alaikum dear students. I welcome you to the 17th lecture of probability and stochastic processes. In previous lectures we have been dealing with continuous random variables which assume values in an uncountably infinite set, which is usually a segment of real line or the whole real line. Specifically, we dealt with uniformly distributed random variables, exponentially distributed random variables, Erlang type random variables, and Gaussian random variables. The Gaussian random variables are very important because they very closely model real life situations where an unpredictable phenomena assumes values which are usually close to a central average value. We looked at a few examples and we are going to look a few other examples. We assumed that a Gaussian random variable has a probability density function which is parameterized by lambda, the parameter, and the form of the PDF we assumed was square root of lambda over pi multiplied by e raised to power minus lambda x square. This Gaussian random variable with this given PDF has zero mean and its variance is 1 over 2 lambda or 0.5 divided by lambda. If the variance is explicitly given as sigma square, which is usually the case in your textbooks, then the expression for PDF of a Gaussian random variable is 1 over square root of 2 into pi into sigma square e raised to power minus x square divided by 2 sigma squares. This is a well-known formula and you can look it up in your textbook. It's also possible for a Gaussian random variable to have a non-zero mean, in which case the expression where there is an x square is replaced by x minus mu x whole square, where mu x is the expected value or mean of a Gaussian random variable which has non-zero mean. We also learned that if we transform a Gaussian random variable using a linear transformation, we can change its mean and variance in a predictable and controlled manner. Furthermore, the Gaussian random variable has a PDF which cannot be integrated in a closed form manner, so you cannot have an expression of x which represents integral of PDF. So you have to rely on numerical techniques or previously computed tables to find probabilities of different events defined on Gaussian random variables. And these tables are usually given for zero mean and unit variance Gaussian random variable. But by relying on a properly chosen linear transformation, you can change any Gaussian random variable with any non-zero mean and any value of variance into a unit variance zero mean random variable, and all the events defined for that non-zero mean arbitrary value variance random variable get transformed to zero mean and unit variance random variable, from where you can find the probability of the event of your interest. This will be clear if we work an example, and the example that we're going to work is the same one we were discussing in the last lecture, where we were looking at random variables representing the heights of randomly picked boys and girls from a large population. If you look at your screen, you will see a slide which shows the probability density functions of these two random variables. The blue curve represents the probability density function of the girl population, the height of girl population, and the red curve represents the probability density function of boys population, the height of boys population. Let's first look at the blue curve which represents the height distribution of girls population and try to find probability of an interesting event defined for this random variable. The girl population has been assumed to have a mean value of 165 centimeter. So this Gaussian random variable which represents the heights of girl has a mean value or expected value of 165 centimeter. So the PDF is symmetric around this 165 centimeter. The event that we are trying to work with is the probability of a girl randomly picked having a height between 165 and 175 centimeters. For this random variable which is non-zero mean and not a unit variance, this is the event that the girl has a height between 165 and 175 centimeter, an interval of 10 centimeters. If you remember, this PDF has a lambda of 0.008, which gives us a variance of 1 over 2 into 0.008 or 62.5. So for this Gaussian random variable with mean 165 and variance 62.5, we are going to use a series of linear transformation to make this random variable zero mean and unit variance. And in this process, we are also going to change this interval, which happens to be from 165 to 175 centimeter, to an equivalent interval on that zero mean and unit variance Gaussian random variable. So the first transformation that we are going to use is y is equal to x minus 165, where x is the original Gaussian random variable and y is our new Gaussian random variable. With this transformation, y is equal to x minus 165. The new Gaussian random variable y is zero mean, because if you just subtract a value which happens to be the non-zero mean of the original random variable, the new random variable has expected value which is subtraction of the expected value minus the constant which was the mean. So this is a zero mean Gaussian random variable with variance 62.5. But what happens to the original interval which represented the height of a randomly picked girl being in 165 to 175 centimeter range? With this transformation, y is equal to x minus 165. When x was 165, y is 0. And when x was 175, y is 10. So this random variable y, which is zero mean and has a variance of 62.5, the probability of the event that we are interested in is that y happens to be from 0 to 10. But this random variable y is not yet a unit variance. To get to unit variance, we will make another transformation, we will make use of another transformation which is a scaling. So we will scale random variable y and get a new random variable z. So z is equal to y divided by square root of variance or square root of 62.5, which happens to be 7.9057. So your new random variable z is y divided by 7.9057. If you use this transformation, then random variable z is a unit variance, zero mean random variable. But what happens to that interval of y which started from 0 and ended at 10? The 0 and 10 will also go through the same transformation, where 0 divided by 7.9057 will be 0, but 10 divided by 7.9057 will be 1.265. So equivalent event is that on a zero mean unit variance Gaussian random variable, you are finding the probability of that random variable lying between 0 and 0.265. Now that we have reached here, we can use the tables to find the probability of this event. In textbooks and other resources on the web, there are different types of tables, and there are some other well-known functions like error function or Q function, which represent numerically computed values of integrals of unit variance zero mean Gaussian random variable. The table I used gives the numerically integrated PDFs from minus infinity to a value of x which lies from 0 to a large value, which is not very large, say up to 4. We'll come to the reason why the values are not given for the random variable beyond 4. Anyway, so we took this 1.265 and put that in the table, and it gives me a number which is 0.897. So what is 0.897? It is the integration of this PDF, zero mean unit variance, from minus infinity to 1.265. But we are not interested in finding the probability of an event which starts from minus infinity and ends at 1.265. We are only interested in the probability of an event which starts at 0 and ends at 1.265. But that's an easy thing, because the integration of the PDF from minus infinity to 0 is 0.5. So all you need to do is subtract 0.5 from this value that you obtained from table 0.897, and when you subtract that, you get a probability of 0.397. So 0.397 is the probability that a zero mean unit variance random variable will lie between 0 and 1.265. Equivalently, this is also the probability that a zero mean 62.5 variance Gaussian random variable will lie between 0 and 10, and this is also equivalent to that a Gaussian random variable with a mean of 165 and variance 62.5 will happen to assume a value between 165 and 175. So this is the kind of procedure we use to find probabilities of interesting events on Gaussian random variables. Let's look at another event defined for this random variable representing the height of a randomly picked girl. The event is that the height is more than 185 centimeters. So if x is the original random variable representing the height of the girl, then we are interested in an event that this x lies in range of 185 to infinity. Let's transform this to a zero mean random variable y, and then this event translates to that a zero mean 62.5 variance random variable have a value from 20 to infinity. And if we use the scaling type of transformation where we divide with the square root of variance or the standard deviation, then we get an equivalent random variable which is zero mean and unit variance, and on that random variable the equivalent event is that the number z will be from 2.53 to infinity. So using table you can find the probability of zero mean unit variance random variable lying between 2.53 to infinity, and it comes out to be 0.006, which is less than 1%. So given the model that we assume, which models the height distribution of girl population, it is highly unlikely that a randomly picked girl will be taller than 185 centimeters. The probability comes out to be 0.006. On the slide, you see this as a blue tail on the right side of the blue distribution. The next event that we are interested in is the similar event for boys population, and now we are interested in a boy being taller than 185 centimeters. You know the boys have a mean of 175, so the probability is going to be more, but we want to actually find numerical value of this probability. If you look at your slide, this event is represented by the union of red and blue areas to the right of 185. The PDF representing the random variable of boy's height has a lambda of 0.005 and a mean of 175. The variance for this PDF is 1 over 2 lambda or 1 over 0.01, 0.001 or 100, and standard deviation comes out to be 10. So if x is original random variable, then we are interested in x being from 185 to infinity, where mean is at 175. If we transform this using y is equal to x minus 175, then the new random variable y is 0 mean, and the event has been transformed to be from 10 to infinity. And if you divide with the standard deviation, then the equivalent event on 0 mean unit variance random variable is from 1 to infinity, and probability of that comes out to be 0.159. So probability of a girl being taller than 185 centimeters is less than 1%, but the probability of a boy being taller than 185 centimeters is approximately 16%. So this is the kind of procedure we use, and this is the kind of questions that we address when we are dealing with Gaussian random variables representing real life unpredictable events. So far we have asked questions about Gaussian random variables, and we were working with an example of a population of boys and girls, but we only asked questions which involved only boys or only girls. We did not ask questions like this, that if we pick a boy and a girl randomly from this population, what's the probability that boy is taller than the girl, or the other way around, that girl is taller than boy. We will come to questions like this in a while, but let's first look at an important property of Gaussian random variables. I have talked about linear transformations that we use to transform a Gaussian random variable with any value of mean and any value of variance to an equivalent Gaussian random variable which is 0 mean and unit variance. And any Gaussian random variable with any value of mean and any variance has a PDF which is a bell-shaped curve, where the random variable is more likely to assume values near the mean, where the peak of this hill is, peak of this bell-shaped curve is, and as we move away from this central value, the probability of random variable assuming values there away from the mean are less. So the question is, if we have a unit variance 0 mean random variable, then what's the probability that the random variable will assume value in a certain range around the mean, which is 0. So the questions like this, what's the probability that a 0 mean unit variance random variable will assume a value between -1 and 1, or -2 and 2, or -3 and 3? These questions are very important because you know through linear transformation any Gaussian random variable can be transformed to a 0 mean unit variance random variable. For an arbitrarily mean and arbitrary variance Gaussian random variable, an equivalent question will be, what's the probability that a Gaussian random variable assumes values which are 1 standard deviation to the right and 1 standard deviation to the left of the mean value. So the probability of such an event is important. Similarly, probability of an event where the random variable assumes values from -2 times the standard deviation to plus 2 times standard deviation or minus 3 to plus 3. So these events are important and they are equivalent to a zero mean unit variance Gaussian random variable having values from minus 1 to 1, minus 2 to 2, minus 3 to 3, etc. We can use tables to find probabilities of such events, and you can see on the slide that you are going to see next that I have marked 3 events for such discussion. The first event on your slide is shown in red color, and this represents the probability of a zero mean unit variance random variable having values from minus 1 to 1. And using the table, the probability of this event comes out to be 68.3%. So there is 68.3% probability that a zero mean unit variance random variable will have values from minus 1 to 1, or equivalently any Gaussian random variable will have values from mean minus standard deviation to mean plus standard deviation. Probability of that event is 68.3%. Let's look at the next event, which is that zero mean unit variance Gaussian random variable will have values from minus 2 to 2, and on your slide this event is shown as union of green and red areas, and probability of this event comes out to be 0.954. So any Gaussian random variable will have its values from minus 2 times standard deviation to plus 2 times standard deviation around the mean with a probability of 95.4%. And if we go beyond that, as we have shown you in the slide, and take event which represents probability of random variable having value from minus 3 to 3 or 3 times standard deviation to the left of mean to 3 times standard deviation to the right, the probability of this event comes out to be 0.997. So there is a 99.7% probability that a Gaussian random variable will have its values within minus 3 standard deviation to plus 3 standard deviation around the mean. When we were modeling the population of boys and girls using Gaussian, I told you that even though the Gaussian random variable has mean of 165 or 175 centimeters for girls and boys respectively, the PDF is defined for all values of R, even negative values, even though the heights of boys and girls cannot be negative. But it was a reasonable thing to do, because taking the example of boys, when the mean is 175 and variance is 100, then there is a 99.7% probability that the population of boys will have a member in the range from 145 centimeters to 205 centimeters. There is less than 0.4% probability that a randomly picked boy will be shorter than 145 centimeter or taller than 205 centimeters. So Gaussian random variables represent real life situations where a random unpredictable phenomena is more likely to have values close to an average mean value. The next topic that we are going to cover is the idea of joint distribution. This is similar to the joint distribution that we discussed for discrete random variables. Now we will have more than one continuous valued random variables, and when we take them as a collection of observations, then we'll have vectors of observation. These vectors can be length 2 like pairs, or length 3, length 4, or any arbitrary length vectors. So we will start with 2 random variables, and they come up with situations where a random experiment is performed and 2 real valued observations are made. For example, talking about the population of boys and girls, we can perform this experiment that we pick a boy and a girl, and form a pair of observations which represent their heights, and we take this pair as length 2 vector and work with that. So this collection of all pairs of observation is our sample space or range of the random variables that they take jointly, and they are defined on real plane, xy plane. If one of the random variable is x and the value it obtains is represented by small x, and the other random variable y with values represented with small y, then x comma y is a point in xy plane, and this point in xy plane has a relative likelihood which can be more or less than the likelihood of other points, other pairs of two observations that we can observe. We'll deal with this question of boy being taller than girl or other way around, but we are going to start with the discussion of joint distribution of two continuously valued random variable with a simple example. Let's take an example of a situation where a random experiment is performed, two values are observed, both are real valued, and they are assumed to always happen in a certain finite range, a small subset of xy plane with finite area A. To make things simple, let's start with the situation where we assume that every pair is equally likely to occur. So we have pairs of observations and every pair is as likely to occur as any other pair. And the region where this pair takes on values has area A, then the PDF of this joint distribution, the joint PDF is a function defined on xy plane. It's kind of a surface, it's a kind of terrain. It can be a flat plateau, it can be a hill-like thing, it can be multiple hills, or it can be arbitrary shape like a terrain of a hilly area. So this function, which is PDF, is defined on xy plane, and it can have highs and low points representing different observations being more likely where the height is more compared to other observations which are less likely where the height is less. So we start with a situation where every observation is equally likely and the PDF is a flat plateau, and this flat plateau has a height k, and this height should be such that total volume in this terrain, suppose this hill or plateau is made of sand, so total volume in this sand is 1. So if the area over which this flat plateau exists has area A, then the height k must be 1 over A, so that when you multiply the base area with the height, you get a unit volume of the sand making up this terrain. The slide shows two random variables x and y, where x assumes values between 0 and 10 and y assumes values between 0 and 13. So the total range where this random variable x and y assume value is a rectangular region where x is from 0 to 10 and y is from 0 to 13. So total area of this domain where x and y assume value is 130. So the PDF is a flat plateau, a semi-cube with height 1 over 130. You can define interesting events on this joint random variables, pair of random variables, and one event is shown on your slide, which is shown as a volume in blue color, which represents that both x and y are smaller than 4. So x lies between 0 and 4 and so does the y. Probability of this event is very easy to find because the PDF is a constant height plateau. The probability of any event is the volume of the sand above the region which represents the event. So the region which represents the event has a total area of 16, 4 by 4, and if you multiply this 16 with the height of the plateau, which is 1 over 30, you get a probability of this event being 16 over 130, which is 12.3%. So if you have a pair of random variables which are jointly random and have a joint distribution which is flat over a rectangular region, and you find probability of this event that both of them are between 0 and 4, it comes out to be 12.3%. The joint distribution of these two random variables is usually represented by fxy as a function of x and y, function of two variables. And from this joint distribution, you can have marginal distributions which are obtained from this joint distribution by appropriately integrating with x to get a marginal distribution of y, and with respect to y to get a marginal distribution of x. And it's so easy to integrate this flat volume type of function, and you can see that the marginal distribution of x comes out to be a uniform kind of distribution where it takes on a value of 1 over 10 from 0 to 10, because random variable x is equally likely to occur with any value between 0 and 10. It's a uniformly distributed random variable, so the marginal density of x is a flat function from 0 to 10 with a height of 1 over 10. Similarly, the random variable y has a marginal distribution which is also uniformly distributed, and this distribution starts from 0, ends at 13, and it has a height of 1 over 13. It's interesting to note that the joint distribution is a product of two marginal distributions. So for any point x comma y which is in this rectangular region on the xy plane, you want to find the value of joint distribution fxy, function of x comma y. It is equal to multiplication of fx of x, the marginal distribution of x, times fy of y, the marginal distribution of y. And you know, in the range 0 to 10 and 0 to 13, these marginal densities have a peak of 1 over 10 and 1 over 13. So for any point x comma y with x is between 0 and 10 and y is between 0 and 13, the joint distribution is 1 over 10 times 1 over 13 or 1 over 130 as we started with. So this pair of random variables x and y which have a joint distribution which is a flat plateau over a rectangular region, where rectangular region has sides parallel to the axes. One side is parallel to x-axis, other side is parallel to y-axis. For this case, the marginal densities are integration of joint densities, and joint density is simply multiplication of marginal densities. This is an important characteristic of the two random variables x and y being independent. So if x and y are independent random variables, you can form the joint distribution where you form pairs of observations, one from x, other from y, and the joint distribution is very easy to form. All you need to do is multiply the two densities, one as a function of x, other as a function of y. You multiply the two expressions, you get a function which is a function of x and y. You get an expression which is function of x and y. This is a function defined over xy plane. It is a function of the form z is equal to function of x comma y, a surface, a plateau, a terrain defined over xy plane, and it represents the joint distribution of two random variables. It's easy to confirm that for this case, where the joint distribution is a flat rectangular plateau with sides parallel to two axes, that x and y are independent of each other. By taking the same event where x and y both lied in the region 0 to 4 and 0 to 4, and defining conditional probabilities for this event. So let's look at unconditional probability of x lying between 0 and 4. The probability of this can be found from the marginal density, and it's easy to find that it is simply 0 to 4 with a height of 110. So probability of x lying between 0 and 4, the unconditional probability is 0.4. Now let's find the conditional probability of this event, that x lies between 0 and 4 given that y lies between 0 and 4. We need two things: the joint distribution of these two events, and from that we need the joint probability of this event, that x lies between 0 and 4 and y lies between 0 and 4. And we also need the probability of y being between 0 and 4, that is the probability of conditioning event. We have just found the probability of this joint event, which comes out to be 16 over 130. And it's very easy to find the probability of conditioning event, that is y lies between 0 and 4, which is 4 over 13, because the marginal density of y is a uniform density from 0 to 13 with a height of 1 over 13. So you divide the probability of joint event, which is 16 over 130, and divide it with probability of conditioning event, which is 4 over 130. If you simplify this division, you again get 0.4. So these two events are independent. So the random variables x and y are independent if the joint distribution, the joint probability density function, is a product of two marginal density functions. I hope you can recall the example we talked about a few lectures ago, where we talked about two trains coming to a central station and people entering and leaving the station and having to wait for certain times. And we assume that one train had a waiting time which lied between 0 and 10, and the other train had a waiting time which lied between 0 and 13. So this joint distribution, which is represented by flat plateau with sides parallel to the axis, exactly represents that real life situation where two observations were made about the waiting time for first train and the waiting time of second train, and this pair occurred in range 0 to 10 and 0 to 13, and all these observations, all these pairs of observations were equally likely because the arrival of one train was independent of arrival of the other train. So the PDFs, the marginal PDFs, the joint PDFs, everything can be related to a real life situation where two observations are made about two aspects of an unpredictable phenomena, like arrival of two trains on a central station and amount of time that we have to wait for first train going north-south and the second train going east-west. The next example that we're going to talk about will not refer to a real life situation. We'll just start with a joint PDF, and that joint PDF is shown in the slide. This PDF is also flat. It looks like a plateau, but this plateau has sides which are not parallel to the axis. You can see from the slide that this is a diamond-shaped flat plateau. The sides are parallel to 45-degree line and 135-degree line. The corner of this diamond-shaped flat plateau occur at 5,0, 10,5, 5,10 and 0,5. And the total area of this flat plateau, total base area, is 50 units. So height of this flat plateau must be 1 over 50 or 0.02. You can define interesting events, and one interesting event is shown on your slide in blue color, and this event represents the event when both x and y are smaller than 5. So they can take on any value, permissible value, but none of the two values is larger than 5. It's easy to find the probability of this event because this represents exactly 1/4 of the total volume of this sand plateau. Hence, the probability of this event for this particular joint PDF is 25% or 1/4. You can certainly find the marginal densities by integrating the volume in this plateau along x-axis and along y-axis. If you integrate with respect to x, you get marginal density of y, and if you integrate with respect to y, you get marginal density of x. Even though this diamond-shaped plateau is a flat plateau of sand, if you integrate to get marginal densities, you will not get uniformly distributed random variables. So marginal densities of x and y do not represent variables of uniform kind. Instead, these marginal densities are triangular in shape. Both x and y are assumed to occur in a range 0 to 10, 0 to 10. So the marginal PDF of x starts at 0, goes up, reaches a peak value of 1/5 when x is 5, and then goes down in a straight line fashion to 0 when the x is 10. So is the density of y. So even though the plateau is flat, the marginal densities are not uniform. Furthermore, if you multiply these marginal densities which are triangular in nature, you will not get the original flat kind of joint distribution, which implies that these two random variables x and y with triangular distributions and a joint distribution defined by this diamond shaped flat plateau are not independent of each other. Let's check this dependence between x and y by taking the unconditional event that x lies between 0 and 4. You need the marginal density which is triangular in shape, and if you use that triangular shape marginal density and take area of this marginal density from 0 to 4, and you find that this area comes out to be 16/50. So probability of random variable x lying between 0 and 4, this is the unconditional probability, comes out to be 16/50 or 0.32. Let's find the conditional probability of this event conditioned on this event that y also lies between 0 and 4. Since the density of x and y are same, the probability of this conditioning event is also 16/50 or 0.32. Let's find the joint probability, and it's easy to find joint probability by looking at the area which is under this event where x and y are both between 0 and 4, and this area comes out to be 9/100. So if you take ratio of 9/100 and this 16/50, you get 9/32, which is 0.28. So unconditional probability of x being between 0 and 4 is 0.32, but the conditional probability of x being between 0 and 4, given that y is between 0 and 4, is only 0.28, and these two numbers are different. So important observation is that if the joint distribution is multiplication of two marginal distributions, then the two random variables represented by the marginal densities are independent of each other, and for this case it's very easy to find the joint distribution because you just multiply the marginal density of x and marginal density of y to get the joint distribution of the pair of random variables x and y. Let's talk about another example of a pair of random variables, but now we are going to look at their joint distribution. Previously we have been working with this pair of random variables independent of each other. I'm talking about the pair of random variables representing the height of boys and height of girls in a large population. It is reasonable to assume that if we pick a pair, one boy and one girl, the height of boy is not going to affect the height of girl. If they are picked independent of each other and randomly, then boy will have some height which is not going to affect the height of the girl, and girl will have a height which is not going to affect the height of the boy. So it's reasonable to assume that these two random variables are independent of each other. With this assumption and with the knowledge that we have of their individual densities, we can find the joint density of this pair of random variables, and this can be found by multiplying the marginal densities or individual densities of the two random variables. Let's denote the height of boys with x. So x is a random variable which represents the height of a randomly picked boy. This variable x has a density which has a lambda of 0.005 and a mean of 175. So the individual PDF for x is square root of 0.005 over pi, we'll call it k1. So k1 times e raised to power minus x minus 175 whole square times lambda, which is 0.005. Similarly, if we represent with y, the random variable representing the height of girl, then the PDF of y will be square root of 0.008 over pi, let's call it k2. So it is k2 times e raised to power minus 0.008 times y minus 165 whole square, where 165 is the mean value of height of the girl. The joint density will be multiplication of these two individual densities as functions of x and as function of y. So it comes out to be k1 times k2 times e raised to power minus 0.005 times x minus 175 whole square, then e raised to power minus 0.008 times y minus 165 whole square. So this expression, which involves x and y, is defined for all values of x and all values of y. So it is defined over the whole xy plane, even though x lies, majority of it lies within -3 to 3 standard deviation, and so does the y. So we will draw this joint density in the slide, and we will limit the region over which we are going to draw this joint PDF to -3 times the standard deviation to +3 times the standard deviation around the mean. If you look at the slide, you will see that this joint PDF, which we obtained by multiplying the two individual probability density functions, is a hill kind of shape. So this hill kind of shape defined over a region of xy plane is the PDF of this jointly random variables, jointly random pair of random variables. So any point xy on this plane has a relative likelihood which is represented by this surface, this hill-shaped surface. And now that we have this PDF, we can talk about probability of events which involve both x and y. For example, we can talk about this event that we pick a boy and a girl randomly out of the population. Then what is the probability that boy is taller than girl? Remember, boy is being represented with random variable x and girl is being represented with random variable y. So we are interested in this two-dimensional plane, and we are interested in events where x is larger than y or y is larger than x. And the regions where x is larger than y represents that event where boy is taller than x, and region where y is larger than x represents that event where girl is taller than boy. In the next slide, you will see this hill shape joint PDF, but from a top view. So this hill, when looked from the top, looks like a variable gray area, and the shining tip is the center of this PDF, where the height is maximum, and this happens for x is equal to 175 and y is equal to 165. This is where the mean value of x and mean value of y coincide, and this is the highest point of this hill type PDF. If you look on this PDF from top and draw a line which separates those two regions where y is either larger than x or y is less than x, then you will see that the region above this blue line represents all those points where y is greater than x or girl is taller than boy. Probability of this event can be found using numerical means, but all you should look now is that this region only takes less sand. It is only taking the bottom slope, it is missing the peak. So it is just taking a portion of the lower slope of the hill. So this probability is much smaller compared to the other region, which is represented by x larger than y, or points below the blue line, which contains peak and the majority of other parts of the hill. So the total volume in this region below the blue line, which represents a boy being taller than a girl, is much higher than the probability of the other event, which is above the blue line, which represents a girl being taller than the boy. So if you have more than one random variables, you can work with their joint distribution, and their joint distribution allows you to ask more interesting questions which involve both random variables, like the one we talked about, where we were interested in finding if a pair of boy and girl is big, what's the probability that boy is taller than girl, or other way around. We should stop now. Today we have covered Gaussian random variables in greater detail. We have covered how to use linear transformation to transform arbitrary Gaussian random variable to zero mean unit variance so that we can find the probability of different events. We also talked about joint distribution of two continuous valued random variables. In coming lectures, we'll continue with our treatment of continuous random variables, and particularly we'll define the conditional densities, the conditional expectations, and transformation of continuous valued random variables. Till then, I wish you the best. Khuda Hafiz. Wassalamu alaikum.